Christian Schilling. He's from Ludwig Maximilian University at Munich, and he, along with his group member, is carrying out researches in at the interface of quantum information theory and quantum many-body physics, particularly quantum chemistry. And research to analytical approaches complemented and guided by computational studies to gain universal insights into interacting quantum many-body systems. A particular emphasis lies on the concept of reduced density matrices and the ground state problem. And today we'll be talking about entanglement in molecules from quantum resourcing to chemical bonding theory. So with this, I welcome Professor Schilling. It is over to you, Professor Schilling. You can, all stage is yours. You can start.
So thank you very much, actually, for this quite flattering and comprehensive introduction. And I'm actually also very grateful to the organizers, for the invitation to this wonderful scientific event. So maybe I can tell you briefly a bit about the motivation of this presentation. So because of this broader audience, including many students, I decided to provide an introductory presentation, an overview presentation into this concept, this fascinating concept of fermionic entanglement, fermionic correlation. And at the beginning, this means to introduce the most essential concepts. And then towards the end of the presentation, I will give you also some ideas about the state of the art of the research and our research ideas that we have been working on the past 2, 3, 4 years, essentially in collaboration with Stefan Knecht and Zoltan Siboras, and of course, together with one of my PhD students, Lex Sindinger. And this was a very fruitful interaction so far, because even I had to learn these concepts in the first place. And I would like to now take you on a journey, the journey I took to learn all these concepts. Okay, and I want to make a strong case for these quantum information tools, that they are relevant for quantum chemistry, quantum many-body physics as well, while at the same time, there's this ongoing second quantum revolution that we all care about. Okay, so it's a pretty fascinating time. So let's briefly talk about entanglement. You've already heard a lot and doing these workshops here. So a prototypical state in a bipartite system, which is entangled, is the following one, this type of Bell state here. So it doesn't matter how this one particle quantum states for Alice and Bob look like. Just assume, for instance, a spin system or an atom with 2 local states. So the first system, A, is in a state 0, tensor, the second system also in a state 0, and then a coherent superposition with a very similar state where you just replace the local quantum states by some other local quantum states. Okay, as you know, this is a prototypical state which exhibits entanglement. It's a pure state in particular. So from a technical point of view, how do you actually confirm that this state is entangled? Well, as most of you know, one could just trace out one of the subsystems, for instance, subsystem B, and obtain the reduced density operator rho A for subsystem A. And apparently it's not a pure state anymore. It's a rank 2 density operator. In that case, I'm in a mixed state. So the von Neumann entropy of rho A is not 0. And therefore, we typically conclude that this respective total state psi is entangled between A and B. Okay, that's well known. That's fine. But there are a couple of questions. First of all, you may want, okay, what is entanglement really good for? How do we actually define entanglement in systems of identical particles? Because there we have a problem to identify the different subsystems A and B, or even further subsystems. And actually, and this for me personally, the most important point, or really like a technicality, which is very challenging. It's like, how do we actually quantify then the entanglement in case our quantum state is not pure anymore? So it's not a rank 1 density operator, but an arbitrary mixed state. And actually, just to recall this, the von Neumann entropy of the reduced state is not a good measure anymore for the entanglement. And the reason for this is quite obvious, because in contrast to pure states, the mixedness of the reduced state could have now 2 different origins. Okay, it could be still entanglement, but it could be also a consequence of the classical mixedness of the total state, of classical uncertainty. So therefore, you have to be very careful in how to quantify the entanglement through reduced density matrices. So the goal of this overview or introductory presentation here is to answer all those questions with a particular emphasis on the fermionic systems, okay, and also outlining the potential relevance of those concepts for quantum chemistry. So let me briefly comment on the physical relevance of entanglement. So I don't need to dwell too much on this because you have watched many exciting talks here at this event on this, but just to recall it. So in general, from a historical point of view, you could say entanglement is just a fascinating concept, a fascinating phenomenon in striking contradiction to our classical understanding of our macroscopic world. And therefore, this concept is pretty important for our understanding of physics in general. Okay. But then from a more modern point of view, you can say that entanglement provides actually important insights into behavior and properties of quantum systems. I would say the most exciting example would be like quantum phase transitions. And more recently, entanglement measures were also used to study the electronic structure of arbitrary systems, in particular in chemistry. This is exactly the third aspect, that entanglement or these quantum information tools, they could serve as diagnostic tools for describing the structure of quantum states. And there, the idea is not then to describe physics or chemistry, but just to improve numerical methods. I would say a prime example are these matrix product states, whose success, for instance, in one-dimensional non-critical systems, of course, relies a lot on this existence of the area law for the entanglement entropy. So the entanglement scaling is not as bad as for generic quantum states, and therefore matrix product states could describe ground states quite efficiently for such systems. So, but from essentially our point of view as a quantum information community, the most important point is that entanglement and quantum correlations are some of the most important resources for realizing many different exciting quantum information processing tasks. So just to briefly name them, it's like quantum cryptography, and this cool idea of quantum teleportation, super dense coding, and probably even quantum computing. And exactly because of this quantum information theoretical relevance, it's really important that entanglement and quantum correlations in fermionic systems or in all systems are quantified in a so-called operationally meaningful way. So we actually want to calculate numbers which have a meaning for quantum information sciences. In practice, however, it's a different story. In chemistry and condensed matter physics, it just means to trace out a part of your system and plug this into a function which is denoted by S. Okay, typically it's the von Neumann entropy, and that's enough to talk about entanglement in the Hubbard model, for instance. But these numbers that people then calculate, they have not so much relevance for quantum information sciences, which is pretty bad given this motivation of entanglement in quantum information theory. So this is exactly the recent situation. We have two kind of quite separate communities. On the one hand, the quantum information world community and the quantum many-body quantum chemistry community. So in the first one typically restricts to distinguishable subsystems like spins, for instance, okay? So no fermions. And after all, the entire quantum information formalism is extremely abstract. So there doesn't really exist any concrete closed formula for the entanglement, even in the smallest systems, of 2 qubits. Of course, this expresses also the intrinsic complexity of entanglement theory. And this is exactly the opposite than in quantum many-body physics. There one would like to calculate numbers, and the price one pays is that the quantification often is flawed because the foundations are not thoroughly understood. And in general, you can say quantum information theoretical tools are just applied in a rather dubious way. And there's also a hype of entanglement. So it's more important just to calculate some numbers and call it entanglement and then write a paper. Okay, so and these two communities are kind of have like a general perception of these concepts, which are kind of suboptimal, I would say, because if you could bring together these two communities, it would be very exciting. So our goal of our research and my group and of this presentation here is to strengthen the connection between quantum information and quantum many-body physics through the unifying concept of entanglement, which plays an important role in both communities. So this is, after all, as you know, timely, because there's this ongoing second quantum revolution, which is all about controlling atoms and molecules to a much higher degree than ever before to realize quantum information tasks. So therefore, we need a rock-solid foundation for fermionic quantum correlation because our matter is made of electrons in particular. So this is the outline, therefore, of my presentation. So first, I'm going to recall the standard quantum information formalism applied to distinguishable subsystems. Then we're going to apply to fermions. So I have to explain to you what are the subtleties, the caveats, and actually how to overcome them. And then in the last part, we're going to discuss a few examples, like first some analytical examples, and then some real chemical systems. And then I would like to explain to you what we may actually learn from those concepts when we apply them in chemistry. So let's now consider some multipartite system. For simplicity, a bipartite system. Okay, so it should be distinguishable particles. So as you know, the total Hilbert space then for Alice and Bob together, it's just given by the tensor product of the local Hilbert spaces HA and HB. The same is true for the algebra of observables. The total algebra is just given by the tensor product of the local algebras AA for Alice and AB for Bob. And here, due to mathematical reasons, I would say, like to keep it simple, one always assumes finite dimensional Hilbert spaces in this quantum information setting. So no mathematical subtleties. So another important concept which we now can introduce in multipartite systems is the concept of a reduced state. Because when you have a multipartite quantum system, sometimes you don't care about all the subsystems, but only about some subsystems. Okay, so in that case, it would mean, for instance, Bob does not care about the properties of his system, and this would be in this mathematical formalism be represented through an identity observable measured on his subsystem. So let's say only Alice measures an interesting non-trivial observable A hat, okay? And then, of course, as you know, when you write down the trace formula, according to the Born's rule to calculate the expectation value for such a measurement, you could trace out the information about system B and end up with a much more compact formula. It's just like involving the observable of Alice system, her reduced density operator rho A, which is exactly obtained by reducing out the system B. So this is exactly the definition, effectively this equation here of a reduced operator. It's exactly this operator which you need to plug in into this linear form to reproduce the correct expectation value for every choice of local observable A hat. Okay. So of course, in practice, it's a little bit boring if only Alice measures an observable, because you would like to understand, even in physics, like what is a kind of the connection between different parts of your system. So just imagine Alice measures an observable in her system, Bob in his system. So how much are those measurement expectation values correlated or connected to each other? Well, this is exactly measured by the so-called correlation function defined in the following way. So it's like the joint expectation value minus the separate one, the product of the local expectation values, okay? So whenever this quantity is zero, it means that these kind of measurements are independent in the sense of expectation values are uncorrelated. But of course, what's quite obvious from here is if the correlation function vanishes for a specific choice of two observables, A hat and B hat, this of course doesn't imply that the same is true for any other choice of local observables, A hat prime and B hat prime. So I think a very common example that you may know is like the dissociation limit of the hydrogen molecule, okay? You separate the two nuclei, you have one electron on the left side and one electron on the right side. And actually there are no density correlations anymore because you have exactly one electron on each nucleus. But you have spin entanglement, okay? This would be such an example of a pair, A hat and B hat with a zero correlation function. And there's a second pair, A prime and B prime of spin observables, which actually have a finite correlation function. So you can say from a physical point of view, it makes sense to talk about concrete observables because then you pick those which you're maximally interested in. But from a quantum information point of view, it's a little bit unpleasant that everything depends so much on the context. And therefore, quantum information scientists in particular define the concept of uncorrelated quantum states. So exactly in the setting that we now defined, we have a bipartite Hilbert space for Alice and Bob. And now we say a density operator rho AB is called uncorrelated whenever the correlation function vanishes, which means this left-handed side is equal to the right-handed side. But now really important for every pair of local observables A hat and B hat, okay? And the respective set of all those density operators which are uncorrelated is then just denoted in the following by D0, okay? Whenever a density operator doesn't belong to the set, we say it's correlated. So now maybe one comment you may wonder, okay, why don't I write down how such a state look like? Well, if the algebra of observables for Alice and Bob comprises all the mathematical operators on the Hilbert space HA and HB, you can say a density operator is uncorrelated if and only if rho AB can be written as a tensor product of the reduced states. But when we apply this to fermions, there's one caveat, namely the algebra of observables is not given by the set of all the operators on the local Hilbert spaces because of a so-called superselection rule. This is the reason why I wrote down this statement about uncorrelated states in a slightly more abstract way. Another important aspect here is now in quantum information theory to quantify the correlation. It's not only important to understand which states are correlated and which are not correlated, but we also want to know how strongly is then a state correlated. Well, by referring to exactly this definition here, we could actually say, let's quantify the correlation I in a quantum state rho AB by just comparing the distance of our state rho AB to the set of uncorrelated states. This is exactly the definition here. So you see, D0 is a set of uncorrelated states. We use here some type of generalized distance functions, the so-called quantum relative entropy. It's a very neat quantity because it has a very clear quantum information meaning, okay? So it's given by some trace formula, and you can say this quantum relative entropy quantifies effectively how difficult it is to distinguish the state rho AB from the state sigma AB. And here we minimize this distance with respect to all uncorrelated quantum states sigma AB in the set D naught. Okay, so actually what's quite remarkable here is you could execute this analytically for every choice of rho AB, and what you obtain is exactly the so-called mutual information formula. So you can determine the closest state. It's just given exactly by rho A tensor rho B. So this is a pretty fortunate factor and a consequence of this very beautiful quantum relative entropy formula. So in other words, you could say the total correlation quantifies the additional information content in the total state rho AB, which is not yet contained in the reduced states rho A and rho B. Okay, so it really makes sense from a physical point of view and from an information theoretical point of view. And now actually I can connect this again to the perspective of physicists and chemists who want to talk about concrete observables. So one can prove with not too much effort that now the correlation function for an arbitrary choice of A hat and B hat is bounded from above universally by the square root essentially of the mutual information multiplied by the norms of those observables. So this actually means whenever the mutual information is 0, the correlation function vanishes for every choice of A hat and B hat. So this is exactly summarizing the paradigm of quantum information theory. So quantum information theoretical tools in general, they provide universal insights into the structure of multipartite quantum states, okay? So this means they don't refer to any specific choice of observables, but the statements you can conclude from those quantum information concepts, they are valid in general for every choice of measurements, okay? This has a huge advantage. So now you may wonder, okay, how about entanglement? Okay, let's have a look at the classical combination of uncorrelated states, the so-called mixture. So this is like the prototypical state, like a mixture in a bipartite setting. So you just take a classical mixture with some probability distribution pi of uncorrelated states. So apparently this is now correlated, I mean, but actually is it also entangled? Well, of course not, because what it means is you have a classical probability distribution, okay? It's like rolling a dice, okay? And depending on the outcome, your system is in a state rho AI tensor rho BI, and this is also uncorrelated. So it's classically correlated, but not entangled. Because of those considerations, which are actually taken in quantum information theory to a next level, in a very sophisticated level in entanglement theory, you could actually now define what you mean by an unentangled state. So a total state, just recall this, a total state rho AB is called unentangled, non-entangled, or separable if the state can be expressed as a convex linear combination, a classical mixture of uncorrelated states. Or in a geometric mathematical way, you could say a state is called unentangled if it lives in the convex hull of the set of uncorrelated states D0, so which is denoted then by D separable. Otherwise, it's then called entangled. Again, now we can restore to this beautiful geometric picture and the quantum relative entropy to define the so-called quantum relative entropy of entanglement, and very nice entanglement measure, which is valid also for mixed states and meaningful. It's just given by the minimal distance measured in terms of the quantum relative entropy of your quantum state rho AB that is given to the set of separable unentangled quantum states dissect. Okay, here, unfortunately, it's not possible anymore to write down a closed formula, because the set of separable states is extremely difficult to characterize, because you need to find an analytical description of the boundary of the set to calculate this minimal distance. And this is not possible anymore for arbitrary system sizes. It's pretty unfortunate, but nevertheless, this definition is meaningful from a theoretical abstract point of view. So let me now summarize these fundamental insights. So here's the state space as a cartoon. Okay, it looks much more complicated in reality. You see here the entire set D of all density operators. Then I illustrated in black the set of uncorrelated states, D0, okay, and then the convex hull in blue, the separable states. So for an arbitrary quantum state rho for Alice and Bob together, the total collation is then just the minimal distance to the set of D0 of uncorrelated states, while the entanglement E of rho is given by the minimal distance to this blue set of unentangled states, okay. Well, in principle, you could also define classical correlated states, but this is like a topic on its own, which I don't want to cover here. But what you can see here is by resorting to these different subsets and this geometric picture, you can define correlation and entanglement in a very clear manner. Okay, so this is like a picture, a geometric picture, which I personally like a lot, and I think it's pretty instructive. Now let's actually apply this to fermions. Okay, so this theory for entanglement measures and concepts applied to fermions is actually, I would say, quite reasonably well developed in quantum information sciences, but often applied in a slightly dubious way in quantum chemistry and quantum many-body physics. So we provided in our recent research articles with Lexin some really broad and didactical introduction to those concepts. So this is a reason why I'm mentioning these two references here to you. I mean, you can find many other references, okay, by many other smart scientists, but here we tried very hard to keep it as elementary as possible, because we communicated those quantum information concepts to chemists and with not a strong background in quantum information sciences yet. So let me introduce some notation. Okay. So first, we always have to define a one-particle Hilbert space H1. Okay, it's a finite dimensional one-particle Hilbert space, for instance, defined by a finite basis set in quantum chemistry for your molecular system, or for instance, a finite lattice in quantum matter physics. Then the corresponding n-fermion state is denoted by Hn. So in first quantized formalism, when as students, we learned that we just need to anti-symmetrize the n particle quantum states for n distinguishable particles with an anti-symmetrizing operator An. But somehow this is a little bit delicate and subtle, because the point is, from a mathematical point of view, you don't want to talk about anti-symmetric wave functions, because this always means you embed your fermionic Hilbert space into a Hilbert space of distinguishable particles, which is from a mathematical point of view not necessary. This is also the reason why in quantum information sciences and mathematical physics, you actually directly talk about the so-called exterior product, the wedge product, the n-fold wedge product of the one-particle Hilbert space. Okay, so this is kind of more the second quantized formalism, and here's more the first quantized formalism. Both are valid and equivalent, but you have to be a little bit careful about the conclusions you're drawing about the first quantized formalism. So then, to actually develop completely this second quantized formalism, we also introduce, if you like, the Fock space F of H1, just given by the direct sum over all particle number sectors Hn. So you can see 0 from 1 up to D, where D is the dimension of the one-particle Hilbert space. So to understand a little bit better how we can express a quantum state in this Fock space, well, let's just introduce the common occupation number basis of occupation number states here. So you introduce some orthonormal basis for the one-particle Hilbert space that you like. For instance, it could be like the lattice side states, could be momentum states in a quantum chemical system, might be like the spin orbitals of your molecular system. So then an arbitrary occupation number state is just given by taking the vacuum and then creating for each orbital 1 to 3 up to D of your basis set a fermion in the respective orbital or not. So N1 is 0, 1, N2 is 0, 1, up to Nd is equal 0 to 1. So you can choose an arbitrary sequence of 0 and 1s, and if you do it for all 2 to the power of D many, you get the entire set of an orthonormal basis. Again, and just to recall, these are the fermionic creation annihilation operators which fulfill the common anti-commutation relations. So now, how do we actually talk about entanglement? Well, the first thing we need to do is in our N-Fermion Hilbert space, we need to identify a notion of subsystems. But we may wonder, where is this tensor product here? There's one really desperate way to find the tensor product, namely to use first quantized formalism and interpret in the first step these n fermions as n distinguishable particles. I mean, this is not very clever, but it will lead to a tensor product. So now you have the tensor product between distinguishable particles, okay? You can group these particles into the first p particles and the last n minus p ones, okay? And then in principle, you could say, let's apply the quantum information formalism of distinguishable particles that I presented to you beforehand. But as you could guess now, the anti-symmetry of the wave function here contributes to the entanglement and correlation. And this is unphysical, because this mathematical entanglement that you would then quantify does not exist in nature. It's a purely mathematical artifact of this artificial embedding of your N-Fermion Hilbert space into the Hilbert space of n distinguishable particles. So this is pretty nonsense, but actually it's done in practice in chemistry since 20 years. A better approach, a more meaningful approach is to use the second quantized formalism and actually quantify not entanglement between particles, between electrons, but between orbitals. So for this, we first actually embed the Hilbert space into the Fock space, okay? And then just imagine, it's just an example, imagine a one-dimensional lattice system on which electrons are hopping, okay? And now you could take this lattice and split it in the middle in two parts, the left half and the right half of the lattice. So now clearly the Fock space of the system can be written as a Fock space of the left half of the lattice and the Fock space of the right half of the lattice with a tensor product in between them. And this gives rise to so-called motor-orbital correlation and entanglement. This is pretty meaningful, and it's exactly the type of entanglement you need to study to understand the success of DMRG in fermionic quantum systems. But here's one caveat, namely a so-called superselection rule applies, which reduces the algebra of observables on those subsystems. We're going to discuss this in a few minutes. So let me actually briefly comment again on this tensor product. I mean, where does it come from? I mean, is it so obvious? Well, actually, I would say yes. So this is the tensor product which I anticipated on the previous slide. So where does it come from? Well, take a basis state, okay, of your total Fock space with n1, n2 up to nm, nm plus 1 up to nd. And now we want to cut the system exactly in the middle into the left half and the right half. So we explained the split now on these basis states. Okay, this would define the tensor product on a global level. So for this, actually, you just split this mathematical object, this cat in the middle, and just say, okay, this is the occupation number state for Alice. This is the occupation number state for Bob, and that's it. So this definitely works, but you can actually even generalize it. You don't need to have like a physical lattice. You could just take a one particle Hilbert space, split it in two parts. Let's say the first few basis states and then the remaining ones. And then this always gives rise to such a tensor product. Maybe one important aspect is kind of this tensor, this isomorphism. This should be actually an isomorphism here from a mathematical point of view. It's kind of highly non-unique if you don't take into account the so-called superselection rule, okay? But let me now exactly comment on this caveat. What do I mean by superselection rule? Well, there's one rule of nature, which is known, I think, since at least the 50s. So nature does not allow one to coherently superpose even an odd particle number states. So this means in nature, you can never ever observe a coherent superposition of a vacuum state and a single electron state, for instance. This is not possible, okay? This is exactly the superselection rule. So from a mathematical point of view, this means the algebra of observables that Alice and Bob could realize or measure in their local labs is actually not given by all the bounded linear operators on their respective Fock spaces. It's given by a subalgebra. It's given only by those observables which are block diagonal respect to the even and odd fermion number sectors of our Fock space. And actually, you could even go one step further. Sometimes, if you want to consider a non-relativistic setting, which is, I would say, quite realistic in chemistry, because in chemistry, you don't want to assume that electron pairs are created from vacuum fluctuations. Then the relevant observers are even block diagonal with respect to every particle number sector Hn. Okay, this is then a so-called particle number superselection rule, so-called NSSR, rather than a PSSR. And from a practical point of view, you could even imagine that experimentalists, of course, cannot realize every possible measurement in the lab because some experiments are really difficult to perform. And then Alice and Bob have even experimentally limited super selection rules. But the take-home message from this one here is the following. There are definitely super selection rules which are applying, okay, which hold true, okay? And because of this, the algebra of observables is smaller than what you would expect. And therefore, the set of uncorrelated quantum states C0 is larger than what you expect. And this is indeed true because of the following consideration here. Just to recall this, we defined a density operator rho AB to be uncorrelated if this following equation holds true for every choice of local observable A hat for Alice and B hat of Bob. But since if these sets A hat and B hat are smaller, the smaller they are, the more density operators rho A, B fulfill, of course, this mathematical condition. Therefore, the set D0 is getting larger, the more restrictive the super selection rules are. And since the set of separable states was defined as the convex hull of D0, the same applies also to separable states. The set of separable states is also getting larger, the more restrictive the super selection rule is. And therefore, the entanglement and correlation are getting smaller when you take super selection rules into account. So this could be also summarized in the following way. Okay, this is like a complementary point. It's like a justification from a physical point of view of the super selection rules, because you may wonder, I mean, sounds very abstract, very mathematical, what I told you now about. I mean, why should we care about it? It's not like abstract, mathematical, esoteric nonsense. Well, actually, no, it's the opposite. If you decide to take the super selection rule not into account, it would mean that superluminal signaling is possible in striking contradiction to the laws of special relativity. So just to explain a little bit like why this extremely strong statement is true, just imagine Alice and Bob, spatially separated in two different planets, could realize measurements of these two observables. You know, they have mission, but you can see they violate the super selection rule because they change the parity locally from even to odd and from odd to even. So if you now calculate the commutator, of course, it doesn't commute, it's not zero. So now it's not very difficult to see that by performing these measurements, Alice and Bob could talk to each other. And if you want to learn a little bit more about this amazing aspect here, just Google for the Twitter account of Lexending, my PhD student. He produced a really nice instructive video which explains a little bit like how Alice and Bob could actually talk to each other by violating the super selection rule. So this shows to you this PSSR, which is ignored in condensed matter physics and quantum chemistry all the time the last 20 years. It's fundamentally important because it violates the special relativity. And just to summarize all these concepts, it's really important to understand that the concept of correlation and entanglement are relative concepts. Okay, first of all, they refer to a splitting of your entire system in subsystems A and B. You could decide on your own what is subsystem A and what is subsystem B. This doesn't mean these concepts are ill-defined. It means they're flexible concepts. You could apply to the left half of the lattice and the right half of the lattice, the splitting. You could, however, also split the lattice in momentum space representation. But what's also important is the concept is also relative in the sense that they depend on the super selection rule. If Alice and Bob can measure only a few observables, the respective entanglement and correlation are relative to those super selection rules. Okay, this is really important to keep in mind there. And again, as already mentioned, there's another important fact which you should keep in mind is whenever somebody violates the super selection rule in the quantification of entanglement or total correlation, one typically drastically overestimate true physical correlation entanglement in a quantum state. And this is actually now also becoming very clear in the following example. I mean, in the first example here. So it's actually a really kind of counterintuitive example. And it's an example of a single fermion. It's the simplest system you can imagine. And many people would even tell you it's kind of nonsense to talk about entanglement in a system of one fermion. Because, I mean, don't you need two particles to talk about entanglement? Well, it's kind of true. You need two subsystems. But here we are talking about subsystems in second quantized formalism. So let's assume now we have a single fermion in a very simple quantum state, a superposition of a left quantum state on the left side of the system on the right side. This could be like the initial quantum state for a double slit experiment for fermionic particle, you know, left slit, a single wave package on the right half of the system. to talk about entanglement, let's express this in second quantized formalism. So now you can actually see that there is a notion of subsystems. So the first entry refers to the occupation number of the left part. So here it's occupied 1. The second side is unoccupied, plus 0 for the left side here, and a 1 for the right one. This actually looks very much like a entangled quantum state, right? So to quantify this in a kindergarten way, we just trace out, for instance, the right part and obtain a mixed state. So we may now conclude, okay, this quantum state seems to be entangled, right? But wait a moment. So we need to be very careful. We're now talking about fermions, and to discuss entanglement and correlation, we need to take the superselection into account. So let's now be a little bit more sophisticated. So I will show to you now the state is actually not entangled. Okay. So for this, let's write down the density operator. Okay. On the total Hilbert space. Okay. So we have 4 terms. So 1, 0, 1, 0, 0, 1, 0, 1, and then this kind of mixed terms. But now to talk about entanglement, we need to recall the definition, and we need to take now into account superselection rules. So in a more straightforward manner, this would mean to say, well, this is the quantum state, and now we want to know, is it now entangled or correlated? Okay. So for this, we need to ask ourselves, what 4 measurements could Alice and Bob perform? Well, we already know the superselection rule applies to Alice and Bob subsystems. So this means we have here the physical algebras of observable AA and AB. But these algebras mean that Alice and Bob could not change the parity of the particle number in their subsystem. But these 2 contributions here, they would correspond to a change of parity from 1 to 0 and from 0 to 1. And for Bob, it's exactly the same. So these contributions, they de facto don't exist if we restrict this quantum state to these local measurements. So this means the quantum state de facto from Alice and Bob's point of view looks like this, okay? And this quantum state is actually a mixture, a classical mixture with 1/2 weight superposition of 2 uncorrelated states, as you can see here. So the conclusion is this single electron quantum state, single fermionic quantum state, is actually mode correlated with respect to left and right, but is not mode entangled. So this again emphasizes the unnecessary embedding of a Hilbert space of an algebra of observables into larger spaces can be quite misleading. Okay, now let's go to quantum chemistry. So you may wonder, okay, if you have a molecular system, how should you actually identify subsystems? Because there's so many different ways to divide the orbitals into subsystems, and you could do it even like beyond bipartite splits. But I would like to emphasize on the 2 simplest ways to split your system, and which actually in turn are even the most relevant ones from a chemical perspective. The simplest one you can imagine is to say, I take all my orbitals and take one of them, one electronic orbital, and then all the remaining ones are subsystem B then. And then one step further, you can say, let's pick 2 subsystems, one orbital I and one orbital J, and quantify then the entanglement and correlation between these 2 orbitals. So let's say we obtain now the molecular ground state of such a system with some computer software, trace out all orbitals except 2 to obtain the 2 orbital reduced density matrix. Okay, let me now briefly explain to you how this guy looks like. Well, it's actually still a complicated object because this is a density operator which lives on the Fock space of 2 orbitals I and J, but we're now talking about electrons. So each electron orbital gives rise to 4 states: vacuum state, 1 spin up electron, 1 spin down electron, and 2 electrons. And then the same for orbital I. So we have here a 16 times 16 density matrix. Okay. And now what is actually illustrated here, many entries are white because this quantum state here has a fixed particle number. So therefore the reduced states, of course, diagonal in particle number representation. But now what's also illustrated is if you take some superselection rule into account, like PSSR or NSR, many further off diagonal entries in light gray or dark gray disappear because Alice and Bob cannot measure them. So this is like, I think, a very instructive picture here. And then to calculate actually the single orbital entanglement, you would even take this guy and trace out the orbital J. Okay. So now you could say we use the chemistry software to calculate the ground state of molecular system, calculate all these reduced states, and now we can discuss entanglement and correlation of concrete systems. So this is like a very simple prototypical system, like a water molecule in a very small basis set. And here we use actually the Hartree-Fock orbitals. These are molecular orbitals as reference bases. Okay, so they're illustrated, in this isosurface plots. Okay, maybe not so important for today, They look very beautiful and cool, I would say. And now I just calculate the single orbital entanglement. So this quantifies how strong is one orbital correlated with or entangled with all the other orbitals. Okay, it seems that maybe some entanglement is quite large, but honestly speaking, if you compare the value here, these are very small numbers, because you always need to compare this to the maximum value of entanglement in such a system. And this is 2 times ln2, which is about 1.4. Okay, so you can say by using Hartree-Fock orbitals, the quantum state looks very much unentangled or uncorrelated. So let's go one step further. Let's look at 2 other systems, like this very nice ethylene system and the very important chromium dimer. The chromium dimer, as you know, is a strongly correlated system. So you can see here, this system here has already a stronger entanglement. Instead of 0.08, it's going up to 0.045, 0.5, and the chromium dimer even reaches almost the maximum value of 1.4. What's also illustrated, and this is maybe a really important message for all of you, is if you take now the PSSR into account, you reduce in all these plots the orbital entanglement from at some value to almost 0. You can see here, you reduce the entanglement effectively to 7%, to 12%, to 12%. So this means in practice, the single orbital entanglement of Hartree-Fock orbitals is reduced by almost 90% on average if you take the important superselection rule into account. This emphasizes how strong the effect of the superselection rule is. So let's go now one step further to the orbital level, because this is much more exciting. It explains actually how each orbital of the system is correlated to every other orbital. So this is illustrated in those plots here. So here again, the H2 molecule. Here I have these 8 orbitals. You see orbital 1, 2, 3, 4, 5 up to 8 illustrated in this cartoon. Okay, and for each orbital we draw a line or curve which explains how strong is this correlation or entanglement. Okay, so here you have the total correlation in the first row. Then actually here is the entanglement in the second one and the classical correlation. And now what you can definitely see here is the total correlation is essentially classical correlation, because the entanglement in this plot here is very small compared to classical correlation. But again, what you have to admit here, if you take into account that maximal entanglement or correlation means black or purple in color, the entanglement between any 2 orbits is almost 0. You know, it's like yellow or orange. And you can again see the superselection rule, PSR or NSR, is further reducing the entanglement. Here it's almost 0. You know, the entanglement with NSR. Of course, if you use the chromium dimer, consider the chromium dimer, which has much stronger correlation, you actually now get a much more exciting plot. You will see now there are at least some orbitals which are strongly correlated. But again, if you go from the left to the right, you see the effect of superselection rule. On the level of the entanglement, is pretty amazing. You kill almost all of the entanglement. So this is, I would say, the true physical plot of the entanglement between Hartree-Fock orbitals. But now there's one crucial aspect which I didn't discuss here. I mean, we always emphasize everything is relative, you know. It depends on the orbitals you consider. So what is now the role of the orbital reference spaces? Or let's take a more constructive quantum information point of view. Can we kind of optimize these orbitals to maximize the entanglement? Because this is what we as quantum information scientists want to achieve. We want to maximize the available entanglement, the available resource of molecular system. And clearly, if we use the Hartree-Fock orbitals, we have seen in the previous plots, even for the chromium dimer, when we calculate entanglement with superselection rules, we almost obtain a very small number. It's like maybe about 10% of the maximum value that you could expect from a system. So this is pretty bad for quantum information sciences, such a low entanglement. So let's now use different orbitals to get high entanglement. And this is actually possible. So let's briefly recall what is a covalent bond, because there's a strong connection between maximizing entanglement and understanding chemical bonding. So to obtain a single covalent bond in this textbook example of a hydrogen molecule, you have a 1s orbital on the left side, on the right side with some single orbital energy, okay, like on this level, okay. And now you bring these 2 hydrogen atoms together to form a H2 molecule. And as you know from your undergraduate studies, you obtain then a bonding orbital by superposing them in a specific way, the phi left and phi right, you know, to maximize the electron probability between the 2, you know, the electron probability between these 2 orbitals. So you superpose them with a plus sign, you can see in between, now you have a higher density when you superpose them with a minus sign, the phi left, phi right, you get a different orbital phi bar, the so-called anti-bonding orbital, which minimizes the electron density between the two nuclei. So if you now switch off the interaction between the electrons, you can write down the ground state of the system for 2 electrons. It's just given by the vacuum, and then put 2 electrons, a single electron pair in this bonding orbital. This is now our quantum state, which is also very similar to the exact interacting quantum state, because this interaction effect in chemistry is sometimes not so strong. So now let's quantify the entanglement. Okay, but now we've again the problem, because everything is relative. So what actually are we talking about? Well, first you can say, well, we want to talk about the atomic orbitals, because atomic orbitals are kind of correlated. This is what chemists tell us when you have a single covalent bond. But can we really talk about the quantum correlation between the atomic orbitals? Actually, no, because unfortunately, these atomic orbitals are not orthogonal orbitals. So therefore, you don't have access to a notion of subsystems between atomic orbitals because they're not orthogonal. Well, what else could we do? Well, we could do exactly what we did before. We can use the Hartree-Fock orbitals. This would mean to use the bonding and anti-bonding orbital, phi and phi bar. Yes, these guys are orthogonal because Hartree-Fock automatically orthonormalizes these molecular orbitals. But again, how does the quantum state look like? In second quarter formalism, the quantum state is given by doubly occupying the bonding orbital and not occupying the anti-bonding. So now we are talking about this tensor product here, and therefore it's unentangled. Pretty bad news. This is essentially the news we already had from before. Like if you use Hartree-Fock orbitals, the entanglement is almost 0. And here in this oversimplified example of non-interacting electrons, it's exactly 0. So here's now the key insight. Take the bonding and anti-bonding orbital and implement a kind of a 45% rotation, a unitary rotation, to get some type of atomic-like orbitals. You could say you take these orbitals and orthonormalize them without changing too much their shape. So you obtain phi L and phi R. Yes, you have then subsystems because these two, the blue and the red orbital, are orthogonal. You can write down the quantum state. Okay, it's just a very simple calculation. And if you calculate the entanglement, you obtain LN4. LN4 is exactly the maximum entanglement you can have in such a system between 2 orbitals, because each orbital gives rise to a 4-dimensional local subspace. So you could say now, if the 2 extremes, Hartree-Fock orbitals give rise to minimal entanglement equals 0, the atomic-like orbitals give rise to the maximum entanglement, which is 2 times Ln2 or Ln4. Let me now briefly comment now on this potentially groundbreaking insight here. Like, we could actually observe that there's a relation between maximum entanglement and bonding order. So typically in chemistry, chemists say a chemical bond means the occupation number of all the bonding orbitals minus the occupation number of the anti-bonding orbitals divided by 2. I mean, this is exactly the formula for the bonding order. So if you now relate this to what we had before, you could say, let's look at this example, this example here for different particle numbers. So here's a 1 electron, 2 electrons, 3 electrons, 4 electrons. This is the state we studied, okay? Chemists will tell you, okay, this means a single covalent bond. If you have only 1 electron, it means half a covalent bond. If you have 3 electrons, this guy will counteract the bonding orbital, and you have again a half a bond. And if you double occupy the anti-bonding orbital, you get 0 bonding. But what is our quantum information formalism telling us? Well, the entanglement in the Hartree-Fock basis is always 0, apparently. How about the entanglement in the atomic-like orbital? Well, here we already have 2 times Ln2, and if you do the math, you obtain here Ln2, 0. So here, the amazing insight is that the entanglement between the left and right, this is a very simple number we can calculate with quantum information tools without understanding anything about chemistry. We just need to split our system in respect to left and right. This number gives actually rise to a quantitatively sophisticated definition of chemical bonding order, because actually here, this, to you, maybe it also looks like a very nice formula, this one here. But there's actually one big problem. If I give you a quantum state, a explicitly correlated quantum state, yes, if I tell you what are the bonding orbitals and what are the anti-bonding orbitals, you could calculate on a computer these 2 numbers and get a fractional number for this bonding order. But the big problem in practice is it doesn't really make sense to separate all Hartree-Fock orbitals or natural orbitals into fully bonding and anti-bonding ones. You could imagine some bonding orbitals more bonding than others. And there are also some bonding orbitals which are neither bonding nor anti-bonding. So it's kind of a really qualitative definition of a bonding order. But with this quantum information perspective, we can define bonding order in a quantitatively meaningful way. And let me actually now briefly also illustrate this localization scheme on the level of the polyethylene system. So just very briefly, this again, the single orbital entanglement for 3 different bases for the same ground state of the same system. So here are the Hartree-Fock orbitals. You can see they're very much distributed over space. So you get very kind of quite small entanglement. Now you could do what actually some chemists try to do is they wanted to localize these orbitals. They use the so-called Pipec-Massey localization. It sounds very promising because it contains the word localization. But if you understand what chemists want to achieve, they don't want to have single-centered molecules because they want to talk about bonding structures. So therefore, if you apply the scheme, you don't obtain single-center molecules or orbitals. You obtain 2-center orbitals. And actually, if you then calculate entanglement with respect to this kind of, I would call it semi-local basis, you obtain even very small entanglement again. So you need to apply our scheme to fully localize these molecular orbitals to single centers, as it's shown here. And then you can see what's happening here. The entanglement, the true physical entanglement is boosted to the maximum value, Okay, here, if you take superselection into account, it's not obtained. You don't push it to the maximum. But you can see the effect of localization is drastic. You tremendously increase by a factor of 10 the entanglement. The physical entanglement shown in black and the mathematical fake entanglement violating superselection rule in gray. Okay, so this emphasizes the tremendous effect of localizations, and it emphasizes that if you localize orbitals, you could increase the quantum informational resourcefulness of molecular quantum systems. I would say this is a key message of this presentation on this research here. And again, just very briefly, just as a cartoon here, again, this system here in this orbital picture, you see here the Hartree-Fock orbitals on the left side. The numbers are like quite small because you have yellow and orange as colors. Then you use Pipec-Massey localized orbitals. Again, it's kind of getting a little bit stronger, a little bit more localized in entanglement and collation, but still a little boring. And now if you go to our atomic, fully localized orbitals, the numbers are exploding. You get really like black, and these black structures are exactly the single covalent bonds which you have in those systems, because these are about the pi bonds. You always have a pi bond between 2 neighboring nuclei. This exactly, the fully localized picture is the picture you need to restore to maximize the resourcefulness of molecular systems, but also to understand chemical bonding structures. So let me summarize this. So we learned how to apply the quantum information formalism to fermions. There are a couple of caveats, okay? And this gives rise directly to the concept of orbital entanglement and correlation. Then because of the second quantum revolution, we have to take into account the superselection rules to quantify, namely, the entanglement in an operationally meaningful way, to get numbers which are relevant for quantum information sciences. Then with our research in the recent 2 years, we established a quantum information toolbox for quantum chemists and quantum many-body physicists. And this is a second highlight, I would say, of our research of the past 2 years, is we found the following insight, namely that a single covalent bond is equivalent to an entanglement content of 2 times Ln2. Okay, now I talk about the mathematical entanglement, this fake entanglement. So this would actually give rise now to a generalization of valence bonding theory or chemical bonding theory in general. You don't need any chemical insight anymore, but you can just apply quantum information concepts to calculate the bonding structure of a molecular system in a quantitative way. So I would also like to use now this opportunity to very briefly advertise some postdoc and PhD positions in my research group. So to learn a little bit more about our research, also about our complementary research on other topics, please check out our research group website. You can easily find it by searching for my name and Quantum or LMU. So I would like to thank you all for your attention, and I'm very much looking forward to your questions. So thank you very much.
Yeah, thank you, Professor Schilling, for your very informative and detailed talk. I am sure that the audience will be very much beneficial from your talk. So now it is open for questions. Yeah, there is some question in the chat box. Are you able to see the chat box?
Yeah. Let's see.
Yeah, there's one question, or if not, then I can read out for you.
Okay, just reading it. Okay, so is it simulation work or actual experimental work of orbital collision measurements? If it's actual experimental work, then which instruments are used? Yeah, so this research which I present here to you today, I mean, it's like, first of all, on a foundational level. So I'm just aware of just a few experiments where they're now trying to kind of realize, for instance, teleportation tasks in fermionic systems. But in general, I would say this application to chemistry is more like an anticipation of what's maybe going to happen in the future. So I'm not aware of any kind of experiments in quantum chemistry where you actually make use of this entanglement yet. But actually, because of the second quantum revolution, which is all about exploiting the quantumness, of molecular systems and atomic systems to their full potential to realize quantum information processing tasks. So the hope is at some point, when you use this molecular systems now for some tasks, I don't care about which tasks for which tasks these molecules are used for. We feel that these quantum information quantities are relevant, of course, because this is exactly what this quantum nature is about. So if somebody proposes an experiment or a quantum information processing task using the quantum nature of an atom or molecule, it's not unlikely that exactly those collation structures of a molecular system will play a role. But to use a molecular system as an entanglement reservoir, this might be actually pretty tricky, because what you have to admit is at the end is there's a system, there's a reason why such a molecular system is in the state that it's in. It's exactly that it wants to minimize its energy. Therefore, it takes the form of an entanglement quantum state. And then to extract entanglement would mean to break the entanglement, right? You need to apply an extraction protocol to transfer this entanglement onto a quantum register. And this would mean to destroy the entanglement in the molecular ground state. But the molecular system is not so happy about doing this. So the experiments I would kind of be looking for is more like where you take even the molecular system as like a quantum computer, for instance, or where you just execute some task within the molecular system, for instance, by using spin entanglement in a complicated biomolecule or some molecule or even biophysics. But this is I think, a topic for the future. And our work should just provide the foundation and provide some ideas how molecular systems could serve as an entanglement resource or as kind of a system to store information or to process information. And to also emphasize the important aspect of locality. So it's more like foundational.
Yeah, there is one more question in the chat box.
Yeah. So can we consider quantum correlation due to symmetrization physical? So exactly, this is a point of this presentation here that depends a bit on what you mean by symmetrization. So if we resort to the anti-symmetry, then the answer is actually no in general. So you have to ask yourself, what is your algebra of observables? And then you need to ask yourself, is there actually entanglement if you take these algebras of observables seriously into account? And if then there's entanglement, then they're good news for you. But if the entanglement is only due to the anti-symmetry, then the answer is no. But the point is, you could also ask yourself, it's like there's some other type of symmetrization. It's not only because of the anti-symmetry for fermions or symmetrization for bosons, but it could be also like translation symmetry or spin symmetries. And if Alice and Bob are not able to break some physical symmetries beyond anti-symmetrization for fermions, then of course the same rules apply. If you have a super selection rule for Alice and Bob, let's say if Alice and Bob have both access to a benzene ring and they can measure only translation invariant permutation symmetric observables locally, you need to take this into account as a super selection rule, and this will further reduce your entanglement. So you have to be always careful. But I think the good point of this more analytical abstract quantum information formalism that I introduced or presented here to you is that you have now a formalism to answer all these questions by yourself. You can apply it and then calculate these numbers in practice. And it's not like rocket science anymore. You decide first as an experimentalist, what is your algebra of observables? What can you measure? What are the restrictions by nature, by God, or whoever? What are your own restrictions as an experimentalist, because you cannot measure every observable? And then after having answered those questions to yourself, you could actually then calculate the entanglement on a computer of the ground state, or measure it, So this is a universal formalism. You can now answer these questions now, given this abstract perspective. Okay, next question, how would you like to advise a student to begin if he wants to go to quantum many body physics and to do the work you are doing. So, I mean, there are many nice papers, I mean, to read. For instance, you can read all our papers, because actually we spend enormous effort to explain these concepts to quantum chemists. So I would strongly recommend to you to read the first half of all our papers of Lexending, which you can find also in the archive. They're written, I think, in a didactical way, because we wanted to communicate this concept to quantum chemists, you know, and even a very competent, smart quantum chemist professor, his background or her background in quantum information sciences is not stronger than the one of a undergraduate student in physics, maybe. So I think these kind of introductory documents are pretty useful. But there are also many seminal papers. Even I've seen like Vlatko Fitral gave a very nice presentation, okay, on a different topic, but he has also many nice papers. So also the papers which are cited here by other researchers. Okay, Vlatko Fitral was one of them, Ignace Sirake, their co-workers. And actually we also cited in our papers many of those seminal references on the superselection rule, for instance, by Nikolai Fries, Bartlett, Weismann, and so on. So just check out these references I provided, check out our papers, and check all the references in those papers. And there are many good papers. So I would just read many of those papers to get an idea. And then it's actually a decision at the end that you need to make. Do you want to go more to a quantum information direction? Do you need to go more like quantum chemistry, quantum many body physics? There are many different perspectives. Also this numerical work, because as I told to you at the very beginning, there are many different reasons why people should care about entanglement. Some people work on the foundations of quantum mechanics, like particularly in quantum information theory. There are many foundational people. They just care about like philosophical aspects in particular. So they care more about Bell inequalities, for instance, philosophy, and so on. Then there are people who talk about chemical bonding and phase transition. So I would say these are the real quantum many body physicists, the chemists. There are some people who do numerics to improve numerical schemes, like DMRG. They care more about the diagnostic aspects. And then the quantum information scientists like us, all of us here, or most of us, who care more about the quantum information processing task. So these are 4 different directions, which are all exciting, and depends, of course, on you, which direction you prefer. So I think these were like, let me see whether, I think these are now the questions in the chat so far.
Yeah.
Are there any further questions? So it seems not.
If there's no other questions, then let us thank the speaker once again for his beautiful talk. So, and thank you very much for delivering your talk in this program.
Thank you.